Okay, so today we're going to look at Zener regulator problem, okay, design problem. So, share. All right. So this is a standard kind of problem. It's similar to the homework problem, but we're going to go a little bit more in depth, and I want students to take out your calculators, and so you can work this problem. Okay. All right. So we are given that this is a ideal Zener diode with a value of 5 volts. Okay, 5 volts. VZ is 5 volts. VL hence is also 5 volts, because VL is equal to VZ. VS can vary from 10 volts to 14 volts, and IL can vary from 50 to 100 milliamps. All right, 50 to 100 milliamps. Now, this is slightly different from the homework problem. We're going to look at two different constraints on our circuit. In the first one, we are going to look at determining the value for RS. Okay, determining the value for RS. And we'll look at the extreme case, meaning the worst case scenario when VS it as its lowest and IL would be at its highest. Okay. So I'll wait until you write that down and then we'll begin. Okay. Wish I could make this bigger. All right, so let's take a look. We have a Zener diode connected in parallel to the load. As far as circuits goes, it's rather straightforward. We have a series resistor RS to limit the current going to the circuit. So if you remove the Zener diode from the circuit and find the Thevenin equivalent circuit, we can see that voltage Vs is dropped across RL and RS. Right? This is a Thevenin circuit as seen from the perspective of the Zener diode. So Zener diode is removed, and then you see there's load RL and the series resistor RS. Now Vs can vary from 10 to 14 volts. RS and RL form a voltage divider network. So if it forms a voltage divider network, then the value of RS must be chosen such that the current cannot exceed or cannot go below a certain limit, right? Supply voltage Vs is dropped across Rs and RL. If the voltage across RL increases, then the voltage across RL would decrease. So if you look at the circuit, this is a Thevenin equivalent circuit, and you apply KVL, and Vs is equal to VRS plus VRL. VRL is fixed. It must be 5 volts. That's the whole point of regulation. VRL cannot change from 5 volts. Must equal 5 volts. Right? VRL cannot change from 5 volts. That's given to us. Zener diode 5 volts, VRL 5 volts. So the output voltage must remain 5 volts, no matter what happens to the input. Now, we need to ensure that RS value will provide for an output voltage of 5 volts. Okay. Since RS is going to drop a certain voltage across it, it cannot go below a certain limit. It cannot exceed a certain limit. If your Vs is 10 volts, what is your VRS? Your VRS cannot go more than 5 volts. Make sense? Anyone receive an email about email validation exercise? Input your login details. Never ever do that, okay? That's spam email. Those are spam emails. So we got an emails from ITS yesterday and the last week, and apparently, I don't know, they've been spreading via the student Cal Poly services. So I'm sure it's going to blow up into a big thing. Okay. So do not enter your login credentials anywhere else. Anyway, does this make sense? Your RS cannot drop a voltage more than 5 volts. Okay. If your Vs is 14 volts, then yes, your VRS can exceed 5 volts and can drop up to 9 volts. Okay. So what's the most extreme case? The extreme case is that RS cannot exceed a certain limit. So we need to find the value for RS max. What is the maximum value of RS? What is the maximum value of RS for a supply current, I mean, for a load current that can vary between 50 and 100 milliamps? Okay. So the question being asked is RS max for its extreme or worst case. Okay. So far, so good. All right. What is the worst case, though? There are many different possible states. One of them is the most extreme or worst case. Let's look at the output. Output can go from 50 to 100 milliamps, right? So the worst case is when the demand is at its highest, right? Load is basically, let's say, if you're PG&E, you're supplying electricity or electrical power to your residential customers, they say peak demand is during the evening hours of 5 to 9 p.m. That's the worst case scenario, right? Maximum demand is between 5 and 9 p.m. In this example, that is illustrated by saying that the load current is 100 milliamps. That's when the demand from the load is at its highest. What's the corresponding worst case scenario on the input side? Load current demand is at its highest. What is the worst case scenario on the input side? When the lowest voltage is being supplied. Does that make sense to everyone? That's the extreme case scenario. When the demand is at its highest and the supply is at its lowest, kind of like the housing market right now. Right? Extreme case, worst case scenario. And what is the lowest voltage? 10 volts. So extreme case scenario, max demand and minimum supply. The max demand would be IL max and minimum supply would be VS minimum, which of course is 100 milliamps and 10 volts. Right now, we're not concerned with the Zener diode, not yet. Okay, we simply want to find RS max for a range of IL. So in this case, if your supply voltage is at its lowest and your RL, I mean not RL, sorry, IL is at max, what should be the Zener diode current? If you have the lowest supply current coming into our circuit, and in this case, I'm talking about this circuit right here, okay? If we apply KCL at the top, I can write IS coming from the supply is equal to IZ plus IL. Okay. Supply current coming in gets divided into two branches, IS coming in, IZ and IL, right? Splits into two currents. Now, if supply is minimum, load demand is maximum, what should be my IZ? Should be a big fat egg, 0. Which again, eggs are very expensive nowadays. So I'm sure there's a joke in there somewhere. Minimum, maximum. Okay. Supply voltage is at its lowest. So supply current, IS, is at its lowest. But even in that scenario, we want our IL to be max. So the only way that is possible is if Zener current is at its minimum. Does that make sense? Right. Let me know if you have any questions. Any questions? So far, so good. Right. Okay, so IZ is 0, IS is minimum, IL is maximum. We know the value for IL max, we know IZ is 0, so we can reduce this expression and express it in the form for supply voltage NVZ. Now, IS is the current, is this current that's coming from the supply. It's also the current that's going through RS. So if we wished, we could express IS using Ohm's law. Voltage across RS divided by RS. Again, our goal is to find a value for RS, right? So we somehow need to find an equation that includes RS. And this does. Okay. So IS is VRS over RS. Then what is VRS? Voltage across that resistor RS. We have the supply voltage at one node. We have the Zener voltage at the other node. Vs minus Vz. Or VL. Okay. So IS is Vs minus VL over Vz. And now we can plug that into the above expression and set Iz is equal to 0. So I can write Vs minus VL over Rs is equal to 0 plus IL. And this gives me Vs Rs is equal to, sorry, Vs minus VL Rs minus IL. Oh, that's right. IL is 0.1. So 0.1 RS is equal to Vs, in this case minimum, minus 5. And therefore, Rs is equal to 50 ohms. All right, let's take a pause. Let me know if you have any questions. Did that make sense? Questions? No questions? RS cannot exceed 50 ohms. That's the max value. If RS exceeds 50 ohms, then the current reduces, the voltage drop across RS increases. Now take a look at the left-hand side, the Thevenin circuit on the left side, top left. If RS increases in value, then your V out decreases. Minimum supply voltage 10 volts. If RS increases, then your VRS also increases. And if VRS increases, then your VL drops below 5 volts. And that's why that's a max limit on the value of RS. Okay, that's the max limit. All right. All right, so now let's look at, are there any other questions before I go to the second half? That's the one extreme case. As I said, you want maximum demand and the lowest supply, minimum supply. That's one extreme case. Now let's focus on the Zener diode. Okay, Zener diode also has power ratings, right? Zener diode power ratings can range from like quarter watts to half a watt to 1 watt to tens of watts. So let's say we have this 5-volt Zener diode here, and let's say we have a specific power rating for that Zener diode, 1 watt or 2 watts or 5 watts. So what's the worst case scenario for a specific power rating where the Zener diode wouldn't work? Right? The job of the Zener diode is to maintain the output current constant, right? So in the second half of the example, PZ max is given to us as 5 watts. Maximum power rating of the Zener diode, 5 watts. So if PZ max is given to us, what is the value of RS? What is the value of RS that will maintain the circuit output load at 5 volts? And for that extreme scenario, we would need a minimum value. Okay. So in this case, if PZ max is 5 watts, what is the maximum current that can flow through the Zener diode? It's a 5-volt Zener. P is equal to IV. So IZ max is 1 amp. The Zener diode can sink a maximum of 1 amp. Okay, it can sink a maximum of 1 amp. Current sink as in SINK, it sinks the current through itself to maintain the output current at 100 milliamps. Okay. In this case, we are focused on the Zener diode so that the Zener diode does not blow up. So the extreme case scenario for this would be when Vs goes to max and IL goes to its minimum. Okay. And we again go to that KCL expression. IS is equal to IZ plus IS is equal to IZ plus IL. IZ cannot exceed 1 amp. When is the max IS? Max IS is for max value of VS. Max value of VS is 14 volts. Okay, it's 14 volts. And we already know what our RS is. RS max was 50 ohms, right? That's for the previous one. Now we're trying to find the other end of that RS value. Okay. So if VS goes max, which is 14 volts, supply is at its peak. But load current cannot exceed 100 milliamps. Everything must go through the Zener diode. Okay. The Zener diode must sync through everything. That's when the Zener diode must turn on and sync all of the excess current. But the extreme case is that it should not exceed 1 amp through that Zener diode. So if supply current goes max and output goes to its minimum, that's when the Zener diode would be at its maximum limit. Okay. So actually, let me get rid of that. When IS, supply current, is at its max and IL is at its minimum, that is the maximum rating or the maximum value of IZ. Again, the function of the Zener diode is to allow as much current as it can handle through so that the output current remains constant. So in this scenario, supply voltage goes to its maximum, but the demand is at its lowest. Okay, supply current goes to its max, demand current is at its lowest. That means the Zener diode must be able to pass all of the other current through itself. And the limit on that current is 1 amp. Does that make sense to everyone? I'll repeat one more time. Supply is at its max, demand is at its lowest. And that's the other extreme case scenario. So if supply is at its max, demand is lowest, maximum value for Zener current is 1 amp. Now we need to find the value of RS that will cause that will not cause the circuit from operating. So if IZ max is 1 amp, then IS max is 1 plus 0.05. And that is 1.05 amps. Now IS is VS minus VZ or RS. Therefore, RS, calculate RS for these values. What do we get? Anyone? What value of RS do you obtain? $8.57, yes. RS cannot drop below 8.57. If it drops below 8.57, the supply current would increase and the Zener would blow out. or your load would blow out, either case. Okay, supply current increases, then either IZ or IL must increase. But if there are constraints on both of those, if there is a constraint on the load, the constraint on the Zener, either one could be damaged. Okay, so in this case, again, the extreme case applies to the Zener diode. All right, let's take a pause. Let me know if you have other questions. Yes. So that was given in the problem, and let's see here. So 50 to 100 milliamps. Yeah, that was a constraint placed on the design. Was one more. And it's calculate max power dissipation in RS value in RS max. RS max. So that's basically from above. Calculate maximum power dissipation in the maximum value of RS. Power, of course, is V square over R, right? V square over R. So P max for R is VRS max or VS max minus VZ over RS max. So the first half, we already determined that RS max is 50 ohms. Now, supply voltage can change from 10 to 14 volts, right? 10 to 14 volts. So maximum power dissipation in RS would occur when it's maximum current. Maximum current would be when maximum voltage. Maximum voltage would be when VS goes to its maximum. Supply voltage goes to its max. That's when maximum power dissipation would occur. So VS max minus VZ, which is constant 5 volts, divided by RS max. So what is the value of P max? Anyone? Anyone? How much to get? There's no penalty. Maybe I should put a penalty. 0.18. Oh, forgot the square. 1.62 going once. Any seconds? Any thirds? Okay, I have 3. Sold. 1.62. That's the maximum power dissipation in RS. We finished up very way ahead of time. Still about 12 minutes left. We had a much livelier discussion in the previous section. No, actually finished about 8 minutes earlier in the last section too. So about 4 minutes of discussion. Think over all of it. Let me know if something doesn't make sense or if you have any questions. Okay. Again, first half was sorry, go ahead. Could appear in the final exam. Yeah, sure. Well, now you would know, right? So it's fair game. Yes. Most interesting job I have worked. Uh, to be honest, I've always been in academia. Um, so one of the things I did previously, I was a postdoc research scholar at UCSB. I was working on type 1 diabetes research. And so we were working with insulin concentrated insulin pumps that could be implanted inside the body, intraperitoneal cavity. That was interesting. It was a lot of work. When I was a student more than 30, 35 years ago, I was doing a part-time job uh, collecting surveys from people. This was back in India. And we would have these survey forms and survey questions, marketing survey, and we'd go to different areas in the city, different cities, different towns, knock on people's doors, and ask them if they were willing to provide feedback on certain things. There were certain interesting times when you knock on different people's doors, try to obtain some answers. This was, of course, long before the internet was around. So there were some interesting times. Those two come to mind. Any questions about about a circuit? I'd love to talk all day long, but class time, so until class officially ends. Do the steps make sense? Do the procedure make sense? Extreme case scenarios or worst case scenarios can mean different things depending on what you're looking at in the circuit. If you're looking at for RS within the constraints of RL, that's another scenario, right? When IL changes, we are saying IL changes from 50 to 100 milliamps. That means that RL is actually changing, right? Your load is changing, hence your IL changes. That's why there is a range for IL, 50 milliamps and 100 milliamps. But we are not concerned with the value of RL in this case. We just need IL, and then we have supply voltage changes. And then the other constraint is the rating of the Zener diode. So in the first half of the problem, we were concerned with the variation in supply voltage and the variation in the output current. In the second half, we were constrained by the power rating of the Zener diode. So extreme case scenarios in both cases, but different scenarios. Okay. All right, so we'll end class here today. We'll pick up here on Monday. There's no Friday quiz this week. We'll do the Friday quiz maybe on Wednesday. So it'll be Wednesday quiz or Friday quiz number 6 on a Wednesday. So either be Wednesday or Friday of next week, but we'll have a Monday quiz. Okay, and I'll post later tonight on what topic it would be. All right. So have a good weekend, and I will see you all on Monday.